we have a big office building, and we have an electronic door that opens with a camera. And every time somebody comes up to the door, we want to see, are they wearing a mask or not? They're supposed to wear a mask. If they're wearing, the computer takes a picture of them. We send that picture to a package in Python called OpenCV that interprets the picture and looks for features inside of it. And basically, it determines if there's a mask or not, right? We then take that to a database, we put it in there, and then open the door. That's possible to build in Python. There's all those different pieces that exist. It's possible to take thousands of pictures of people wearing masks and thousands of people not wearing masks, and then figure out which group do you belong to. Does that make sense? Of course, it's very difficult to group people by groups if you're not sure what the categories are. So I have a prediction. You could tell me if I'm right. People who wear hats, and currently there's four people on video here. Karen and Krishna are both wearing hats. Purna and Vin are not wearing hats. What do you think that means? Is it true that Krishna and Karen are smarter than Vin and Purna? I mean, that's true. That's not just a possible. That's a fact. But my point is, how do we know, right? Like, what are the factors that determine what's the difference between them? What's similar between them, and what can we learn from it? It might be that hats have no difference whatsoever, and if we look at all these factors, maybe it doesn't matter. But with enough data on each of them, it turns out that Vin and Purna are super rich, and Krishna and Karen are super poor. That's the weird correlation with hats. You know, poor people wear hats. It could be about grades. It could be about something else, right? It could be that there's many different factors that we could figure out based on enough data. We could also find some very strange things. Do you know that Krishna and Karen are both vegetarian? By coincidence, also happen to be wearing hats. And maybe if we start gathering more and more and more data, we'll find out there's a correlation between hats and vegetarianism. That's nothing I would ever think of to look for. That's completely spurious correlation, but it could be supported with enough data. When it comes down to it, we could either ask the computer to figure out what's going on based on hats, no hats, or we could say, here's some people with hats, here's some people without hats, here's a brand new person, Thuk just showed up. Does Thuk have a hat or not? And the computer will say, well, Thuk's head does not look like Karen's head. It doesn't look like Krishna's head. Based on that sample, Thuk is probably closer to the Purna Vin group because he's not wearing a hat. Make sense? So we could try to cluster people in different groups based on different factors, right? Sometimes clustering can also be used for other purposes. For example, we could use clustering to try to figure out socioeconomic status. So what kind of car do you have? Maybe all the fancy cars go in one group, all the other cars go in another group, and then we could figure out the connection between them. Are there some people who are in the fancier group who have, access to more money because they have Porsches, and the other group has terrible cars? Leader has a hat. Look at that. There you go. Exactly. Leader's in the vegetarian smart group. Surhabi no hat. There you go. You get the idea, right? So we're going to look at building a simple model today, and then we're going to talk about how to build this in Python and other pieces. But the idea is clustering, and clustering using a predetermined set of data. I want to point out something really important that a lot of people make mistakes about. Imagine for a second, I took a picture of Vin, I took a picture of Karen and Krishna and Purna, and I took a picture of Leader, and we took all those pictures. We're not asking the computer to remember a picture. We're not asking the computer to say, is this Leader? Is Leader wearing a hat? Based on data already in the database. We're asking it to take brand new data that does not exist and say, look at Surhabi. Is Surhabi wearing a hat based on what you already know? And then it will come back as yes or no. Does that make sense? So we're trying to find answers with non-existent data. That's the whole challenge, right? And the model that we're going to build is going to come back with an accuracy prediction. The higher the accuracy prediction, the more likely we can be sure that what we're looking at is a certain thing. And we could build these systems to do all kinds of things, from stock prediction to identifying photos to listening to sounds and a million other things, right? So we're trying to look at the commonalities between clusters. And we're going to do a very simple example today, and you'll see how this works. And then we'll talk a little bit more about higher dimensional data and dimensional modeling afterwards. All right, so let's zip over here for a second, and you could follow along with the code. You can just watch. You can ask any questions you have, and then we'll go from there. All right, so This is going to be, can you see the screen? Okay. Yeah, we're good. No screen? No screen? Vin says yes. All right. So we're going to start off with a website called machinelearningforkids.uk. I'm going to click on this over here, and I'll put this link in the chat. You can just give it a click, and you can follow along if you like, or you could just watch mine, and then we'll see what happens. Now, we could do a program like, are you a Vin or are you a Karen? And we could take like a bunch of pictures of both, and then we'll put in a new picture like Serhabi and find out if the computer thinks Serhabi is closer to Karen or closer to Vin. That's not very useful and doesn't really make sense. So instead, we're going to make a new program, and this program is going to identify, we could do words, we could do images, we could do a whole bunch of different things, video, right? We're going to do, I don't know, can you think of an example? Karen, you cannot. Good question, though. And I'll tell you why. Friday meetings, I don't have to be here. This is volunteer for faculty. The program meeting is important because it connects students together, and I don't have to feel bad if I screw things up. I don't have to practice. I don't have to worry about it. In fact, if I make mistakes, I could just blame it on Kevin and leave. So do me a favor. This is my downtime. Will India win the World Cup? Dhruv, you don't even have to ask that question. Of course India is going to win the World Cup. There's no question. Everybody knows that. That's a given. That's not a, exactly. Karen agrees with me. How about we do butter chicken versus biryani? That's a good detector. That's pretty useful. You get some food. You're not sure what it is. You pull out your phone. You press a button, and it tells you if it's butter chicken or biryani. We're going to set that up in a second. Now, there's an app. There's a show. Have you ever seen the show Silicon Valley? All of you should watch it. It's hilarious. I highly recommend it. Silicon Valley is a great show. And in that app, they make if it's a hot dog or not a hot dog. I have the app on my phone. You point it at something, you press a button, and it'll tell you if it's a hot dog. It has a machine learning model trained with thousands of pictures of hot dogs, and it can identify new hot dogs in real life. We're going to build the same program now, biryani versus butter chicken. So here we go. We're going to move over to this site. And we're going to press get started. We're going to go, I'm just going to press try without registering. I'll set up an account. You can do the same thing. And then the first thing we have to do is set up the project. And we're going to call this project biryani. And we're going to recognize images, right? And I'm going to press create. So it creates this container that our project goes into. And in the project, this is for kids, right? But you could do the exact same thing in a Google package for Python called TensorFlow. TensorFlow does the equivalent of everything we're doing today. You could just Google it and go through a code lab notebook. Obviously, biryani and butter chicken are far more exciting than Flowers' Iris dataset that they're going to go through, but you get the idea of how it works. And you could do anything you want, right? So it actually works in Python as well. The first thing we're going to do is called train. Training is going to train the computer to recognize images in different types. I'm going to press where it says add new label, and we're going to make two containers. The first one we're going to make is called biryani. It makes a container for biryani. The second one we're going to do is butter chicken. So I have these two containers. I'm going to put images into each one of them. But just to make the computer harder for the computer, we're going to add a third category. You have an idea for a third category?
Not biryani.
No idea.
No,
but some other food. We want a different thing that looks completely different than biryani and butter chicken. Totally different. But tikka masala looks like biryani and butter chicken. I want something, an Indian food that's not chicken, something different. Some kind of like a drink or fruit or something different.
So
Paneer. That's a good one. Okay, we're going to put in some paneer cheese. All right, so I have 3 containers. And what we're going to do is I'm going to go over here. I'm going to open up Google Images, and I'm going to type in biryani. Okay. And I'm just going to scroll over here. I'm just going to move this page off to the side, but I have it open on my other screen. Let me just resize this a little bit like this. Hold on. Okay, so now the important thing is, like I mentioned, right now, we're not trying to see if the computer remembers. We're trying to see if the computer can be trained to recognize new images. Okay, so you should see my whole screen now. I'm just going to take these pictures of biryani and just drop them in here like this. Okay, so to make this work properly, we need a big enough data set, a sample, to make it work. I'm going to try to do about, sorry, this thing is being difficult. I'm going to try to do about 12 pictures for each one. And if you look down here, there's a number. It says so far we have 7 images. All right, and the more we have, the better. And it's probably a good idea if we use approximately the same number for each container. And I don't know about you, but I had eggs for breakfast like 5 hours ago. I'm kind of hungry now, and we're going to spend an hour talking about food. And this happens literally in every class I teach, so you're welcome. All right, I have 18 pictures of biryani. Next, let's look for some butter chicken. So I'm just going to type in butter chicken, and here's some pictures of butter chicken. And we're just going to resize the window a little bit, just so everything fits a little better. We'll drop that in. Perfect. We'll grab one of these guys, and we'll grab one of these guys. Okay. Now, right away, I could tell you that one of the things that the computer can recognize from butter chicken versus biryani is that butter chicken is a different color. Right? Like if you look at the color profiles, maybe that's the difference between our two groups. The tricky thing about machine learning is that the computer looks at millions of different possibilities, but doesn't tell us why it made one decision or another, right? And we see this happening with like neural networks and other types of deep learning, where there's millions of pathways to get from one point to the other, but it doesn't necessarily tell us why. All right, so we got 18 pictures of biryani, 18 pictures of butter chicken, and next we're going to do 18 pictures of paneer. All right, so here we go. And of course, paneer looks totally different than butter chicken or mango lassi. It's white, there's no rice, it comes in cubes, it comes in different shapes. So far, it's not necessarily in a bowl. This one's confusing. That one is in a red sauce, right? But most of these are, cheese. It's a different color, texture, shape, profile. This one's fried, which is literally amazing. And I don't know about you, but if you haven't had fried paneer, I highly recommend just go out and do that now. It's life-changing. Granted, it could be life-changing sending you to the hospital from eating fried cheese, but it's delicious. All right, let's grab a few more of these. I'll grab one of those. Okay, so we're up to 16, 17, and 18. We'll throw in another one for good luck. There we go. So we have 18 biryanis, 18 butter chickens, and 19 paneers, right? Maybe we'll just make it 20. All right. Okay, everybody with me? Make sense? All right. So we're going to go up here to the top. I'm going to press where it says back to project. The next thing that we're going to do, let me just zoom in there a little bit. And the next thing that we're going to do is we're going to click on where it says learn and test. And this is going to tell us that we have 18 samples of biryani, 18 samples of butter chicken, 20 samples of paneer. The computer is going to look at elements of each picture to find commonalities and build a model of what each one is. What is biryani, as well as butter chicken, as well as paneer, and then start coming up with differences between them. So I'm going to click where it says train new machine learning model. It's going to think about it for a few minutes, and it's going to build this model that's going to have all the information inside, and it says the model is now available, right? We could test this by, I'm going to go back to our biryani page. I'm going to grab a picture that the computer has never seen before, and I'll right click, I'll go to copy image address. Let me just test it. Okay, so this is a thing from Indian recipes. It's a picture of paneer, but the computer's never seen this one. I press run, and it says it recognizes it as paneer with 100% confidence. So that means that we built a program that could distinguish between three kinds of pictures. And we could easily build an app now on your phone. We could put it in Python. We could build it as part of a website that when you put in a picture, it will recognize the difference between butter chicken biryani and paneer, right? If you want to check if this is true, find a picture of biryani on the web, send me the link in the chat. Just drop the...
Cindy, question.
Mm-hmm.
Can we use this to go to let's say a restaurant or a place and take a picture of something and add it to the app, and the app's supposed to tell me if this is real, in this case paneer cheese or whatever we are asking the machine learning to learn?
You can. So the idea of machine learning, or in this case of image recognition, is that it looks at a huge database of what each piece is and can recognize it. Imagine we took this program and we had a conveyor belt of items in a factory, and it had to take pictures of each item and figure out what it is. Now we've trained it to recognize what these different pieces are, and we can sort the items, accordingly, based on the computer being able to now recognize what those models are, right? So here's a picture that Sir Hubby sent in. This is a biryani recipe. Here's a picture of biryani. I'm going to right click on it, copy image address. We'll put it up here in the chat just to make sure it's good. It looks like it's okay. We'll go into here and I'll replace this and press test. And it comes back and says it's 58%, its confidence is buttered chicken. Okay. So what does that mean? This picture has rice in it. It doesn't look a lot like other kinds of biryani, right? So the best way to train the computer to be more confident that this is biryani is by adding more biryani images to train the model more, right? The more training it has, eventually it has enough reference points that it could properly identify what it is. Same thing with people.
Another question, Sidney. Now that you mentioned, I'm sorry. So what would be the threshold? What would be the number? Because right now it's 58%. It's obviously that is not correct, but it is 95%, it is 99%, it is 90%.
Now it's 58% confident. Let's take a look at Krishna's example. So here's one. This is Kudal Paneer. This is one that's paneer, but it looks like something else because it's red. Let's give this a try. So the question is, what's the threshold? It depends on how many images and how many features are in it. It also depends on how things are different. Now this one is paneer, but it says it's buttered chicken, 76% confidence because of the colors, right? Again, if we went back and we trained buttered chicken better and we trained paneer better, eventually it would be more and more confident, and we could do that by adding additional pictures, right? If we went through and added thousands of pictures of one or the other, it would be pretty confident. Of course, if I go and use a standard picture, right? Like if I go here and I say images, I'm going to type in paneer cheese, and I'm going to scroll way down. The computer has never seen this picture before, right? I'll grab something that looks like the ones that we've done before here. I'm going to right click on it. I'll go to copy image address and I'll just try the image. So this is the picture and I put it in here. It says it's paneer 100% confident because it looks similar to the images that we put in before. If we wanted to be able to figure out the picture that Krishna sent, we'd have to train it with many, many more examples that look different to figure out what's the subtle differences between biryani, the subtle differences between paneer, especially when they're different colors, right? Maybe they have different shapes, for example. We could also use the same technology to identify differences between people. So for example, if I took one picture of Kevin, one picture of me, one picture of Karen, one picture of Krishna, and we took a new person, who does Martin look the most like, right? I don't know, Martin's not wearing a hat, so Martin might look the most like Vin. But that doesn't make sense. We really need a lot of pictures of each person. For example, we can go and scrape the social media profile from Facebook of the 1,000 pictures that you put together. Then we could be really confident that if we take a new picture of you, or we have a security camera or something like that, it will automatically identify who you are. Does that make sense? This wasn't my idea. There's a company called Clearview AI. Clearview AI said, what about if we build a database and we web scrape every single picture on the internet, we figure out who those people are, and we build a database that automatically recognizes people. And they got like hundreds of police agencies to use this. It's currently being used. It's a real thing. You can Google it, Clearview AI. And your pictures on social media are probably in there. And if they see you on a CCTV camera, they can identify who you are based on facial recognition using this massive machine learning data set. So it already exists. It is possible to train computers to recognize all kinds of things. For example, is currency valid? Is a passport valid? Is this the person's face? What are we looking at? And so on, right? Using this idea. Now, let's go back here for a second. So we basically built a program that recognizes three different things: paneer, butter chicken, and biryani. I could also do, a webcam, right? So I can test that. And I am 95% paneer cheese, in case you were wondering. So if the computer had to pick between those three options, I come back as paneer cheese. I don't know exactly why this happened. I could try to draw you a picture of biryani, maybe with like some chicken over here and some rice and so on. And that is also 86% paneer cheese. Obviously, I'm not very good at drawing. The point is that we could try to pass in new things that it hasn't seen before and then figure out how to use those. Now, we could also use these as an algorithm, right? In this program, they have make. You can export this to Python. Lately, it hasn't been working very well, but we can give it a try and see if it works. Let's go into Replit, and we'll go into Python here. And I'm just going to copy in all of this code. And I'm going to download this file. Just a second. For some reason, it's not letting me download it. Just give me a sec. Okay. Lately, it's been giving me problems. I haven't been able to get it working, but we'll give it a second. We'll try. Okay, TensorFlow is not installing properly on Replit, so forget that part. But it is possible to run it on the computer. It's just not working well here. But anyways, if you go to make, we could do this in Scratch. We could do this in App Inventor, and you could build a phone app. And we could use our program, enable the camera to test it, right? The nice thing is that there's a section here on worksheets that has like 1,000 different things for kids that can do sorting. It can do all kinds of different pieces. And I'll show you one really quickly for rock, paper, scissors. And let's go to the project worksheet. I'll send you the link to this as well, and you can take a look at it. And we'll build a rock, paper, scissors quickly. If you're in my first semester class, you recently did something like this with coding. And we'll take a look at this project and we'll see how it works. I'm just going to build a new model to make it work. Is everybody on the same page? You understand what's going on? If you have any questions, let me know as we go. Let's go up here. I'll go to the beginning. And we're going to press go to your projects. I'm going to delete butter chicken. And I'm going to create a new project, rock, paper, scissors. We're going to recognize images. I'm going to press create. I'm going to press add. Oops. I'm going to press go into the project. I'm going to press train, add a label, and we're going to make 3 different bins. Okay, so we're going to do rock, and then we're going to do paper, and then we're going to do scissors. Okay. And then to make this work, I'm just going to use the webcam. I'm going to take a bunch of pictures of rock, paper, scissors. So we're going to start over here. I'm going to put my hand like this. Just going to move it around a little bit. So if I move my hand later, it basically okay, so I got 15 pictures of rock. Let's do 15 pictures of paper. Okay, And then we'll do 15 pictures of scissors. And just moving my hand around a little bit, just so the computer recognizes it if I'm doing it in different ways. All right. Done. Thanks for your patience. Let's go back to project. We're going to press where it says learn and test. We're going to train it. Okay. And now that we're done training the model, we'll just give it a quick test. We're going to put a hand in there and it says 43% rock. That's not very good. We'll test it with some scissors. It says 87% scissors. We'll test it with some paper and it says 89% paper. So it is working. Rock did not work so great. And that's because I used a lot of different rocks, but that's 85% confident. So it's pretty good, right? If we want to add some more to make it even more confident, we could just go back here and do a better job of adding some more pictures. Let's try to get it to 20. Okay, paper. We'll add some more paper pictures.
Can you test it with another student's hand?
Sure. Send me, well, I mean, it's really looking at a lot of factors like my background, the lighting, but yeah, it could work. Send me a picture. We'll try it. Okay, I'm going to press learn and test, and I'm just going to run where it says train a new model. And it's just going to update the model. It will say training, and now we have a better one. We'll try it again. Here we go. And it tells me 100% scissors. So it looks like 20 is a better way to go. We'll try it again with rock, and it tells me it's 100% confidence is rock. So we added pictures to increase it to the point where we're good. Again, this is supervised learning because each image in the data set is labeled what it is. Is it a rock? Is it paper? Is it scissors? And then it looks at what are the commonalities between those pieces. You with me so far? All right, so we already did this part. Now we're going to go on to the next part. So let's go back to the project. We're going to press make, and this time we're going to use the program Scratch. And we'll open that up. And Scratch is like a no-code coding platform. We could do this in Python too. And we're going to go down to the one that says rock, paper, scissors, this one over here. Okay. And then we're going to set up a few of the pieces. So we're going to press, let me just open this a little bit bigger. Okay, so we're going to press U. And then here, we're going to say, we're going to go into rock, paper, scissors, and we're going to grab rock, paper, scissors. Each one of these dark boxes is the model that we trained that has those elements inside of it. Okay, and then we're going to say, okay, that's good. And then we're going to put in recognize the image label. And then we're going to put in costume image. So basically, when we show it a picture, it's going to run it through the model. And let's press the green button. Hold on. And then we'll press the P button. That's me. I did paper. The computer did rock. You win. So we actually built a front end to this software. Let's check it out. I'm going to press P again. I did scissors. It told me I did scissors. The computer picked paper. I won again. Let's try that one more time. I'm going to do rock. I did rock. The computer wins. And you'll notice that the computer is telling me what I put in, and it's recognizing it accurately. Right? So every time you press P, I'll do paper. I'll hold it here for a second. I did paper.
And I guess that from here, see that you can make an app.
Exactly. Yeah. I mean, it's currently running on the web and it should work. I don't know if you could open this link. We'll give it a try. Give it a try. Sir said this is recorded. I never said that. Oh, maybe I did. I don't know. Listen, when you get to be my age, you say a lot of crazy stuff. All right. Makes sense? So basically, does it work for you, by the way, when you open it?
No, it's not.
Press the
No,
P
it's not
key.
working.
Press the key to make it work. Let me try it.
No, the code is empty, so we have to do it again. And
Oh, okay. Okay. But anyway, it works, right? You just have to set it up. We'll do paper. There you go. And it knows what I did. It knows what the computer did. And it says it's a draw, right? And this is the basis for making software that does a million different things. Let's take a look at some other examples quickly. And I'll show you some of the ideas that we started talking about today. And it can give you some ideas of what you can do with code, specifically with TensorFlow or other kinds of machine learning. But there's obviously a lot of different examples. And I really like this one of machine learning for kids because it's really easy to get started. Export your code in Python, see how it works and set it up, make sure that it connects all together. And then if it's working okay, build this into something fancier and a bigger pipeline with more code that does different things, right? So let me just grab some slides and we'll take a look. Just 1 second. TensorFlow is a package for Python. You could also use it in other languages, like in R. Obviously, I like Python, but you can do TensorFlow in other languages. So let's take a quick look. We'll go through some slides and we'll talk about some of the ideas behind this. Has anybody here been to Union Station in Toronto? Union Station in Toronto? It's a big train station downtown. Nope. Shade was there. Shade knows all about it. Let's take a look at it. All right. So this is Union Station in Toronto, and it's an old building. It has a lot of stuff on it. It's like 100 years old. There's a lot of very fancy design. If you look carefully, a lot of buildings in Canada don't have this much detail. And even the ceiling is like very complicated with lots of little pieces. And you have architecture students from University of Toronto who are sitting there on the floor, sitting on their jacket all year round, sketching the ceiling, drawing pictures of the building, drawing different pictures of the building, right? Like trying to, trace it and copy the architecture. And the architecture is very complicated. And there's a lot of different details that you could pick up on, right? And really, this is what we're talking about today. The more details you have, the more accurate your model is, until it's too accurate, it's overfit, and then it only works. Marlon before said, can this work for other people? What about if I trained a model that was so specific, it only worked for me, for Sid, and it didn't work for anybody else in the world? Right? What if we trained a model that's so specific, it could only recognize one restaurant's biryani, but it won't work for biryani anywhere else in the world? It's not really useful. So if you spend a ton of time with a ton of detail, you can get a really accurate representation. If you spend 10 seconds doing it, maybe we're going to have something, but we're looking for something in between, right? That's functional enough that we could use in a program, but at the same time isn't overly complicated for the computer to work. And that's what we're going to talk about today, the curse of dimensionality. So the idea is that the more features we have, at some point it works great. So we could look at more and more factors, but then at some point there's a huge drop off in performance. So if I ask you to evaluate 2 or 3 or 4 or 10 factors, that's okay. When it gets to thousands of factors, you just can't think about it anymore. It takes too long. And it takes you 100 years to order a pizza. Normally, you just walk in and order a pizza, right? It takes 1 second. So here's the game. You could type in the chat or just tell me, what do you see on the next slide? Ready? Ready? Here we go. What do you see?
Brad Pitt.
What else? So we start having some really interesting answers. Like, for example, we have a gun, actor, Brad Pitt, blonde. We have fit. There's some cartoons in there from King of the Hill. We also have like a squid creature at the bottom. and a whole bunch of other pieces. But as soon as you look at this picture, your brain tells you Brad Pitt immediately, right? You could start identifying different roles, different movies. You could say Benjamin Button. You could say all sorts of different things, right? But your brain thinks about it immediately. Now, here's my question to you, and this is really what we're talking about today. Did your brain have to think about every actor and every movie you've ever seen in your entire life? Think about all of them and say, nope, that's not Brad Pitt. Nope, that's not Brad Pitt. And eventually say, that's Brad Pitt. No, it just came to you. It just happened in 1 second. Computers don't work like that. Computers have to think through every single possibility, every mustache in the world to finally get to the right one. That's the challenge, right? So we'll take a look at some of those slides. When you look at how many points of data are on someone's face and how facial recognition works, comparing people like between those different data points to match them up to somebody can be really complicated because it uses high dimensional data. That means that you could take a person's face, and depending on which features and which combinations, many people do have similar facial characteristics, but in that combination, it only belongs to one person. So it can create a very complicated data problem. So we'll talk for a second about dimensionality. Here we have the whole population of this summer camp on one line, right? Here we take them and divide them by boys and girls. This is like a two-dimensional array. So Karen, yes or no? Karen wants to know Clearview AI, facial recognition, but what about people with COVID that are wearing masks? Obviously, it's harder to use facial ID using a mask, but the distance between people's eyes and the structure of their face can't be changed even if they get plastic surgery. So that's something that can be detected that can't be changed, right? So if you could do measurements on people's eyes and stuff like that, if they're wearing glasses and a hat and a mask, they may not be able to recognize though. But Clearview AI is used for a lot more. Like, for example, if they see a picture of you from somewhere and then they compare that to a database and can figure out who you are, right? That's the problem. So, and there's another issue. You could look into this if you're interested in this topic. There's a company called Cadillac Fairview. They own malls across Canada. They had a kiosk that you walk up to get information on the stores in the mall. It would take a picture of you and then figure out what your age and profile and stuff like that are. But more importantly, it would take a picture of you and store the data points of your face into a database. And even though it didn't store your picture, it stored your biometric face. You can't change your face. You're stuck with it, right? It's not like changing, your credit card number. So Serhabi says that they ask you to recognize you. That's true. When you go across the border, they ask you to see your face. But the point is that, this was a big controversy because they're taking people's pictures without their consent and using them in ways that they didn't know. And the issue really comes down to, is there implied consent? If you put pictures on Facebook or on Twitter or something else, do you allow other people to use them and basically map your face to take that information? So in our case with the camp, we have a bunch of kids and they have a whole bunch of different characteristics. They're different ages, languages, Aboriginal status, grade, feedback, satisfaction, etc. So if we were to take one-dimensional, the kids on one line, then we would have 20 divided by 10 is 2 samples per interval. If we make it 2D, there's 0.8 samples. And finally in 3D space, and you'll see what this looks like with a hypercube. Basically, if you put everything on one line with 4 regions, we could try to identify population A and B very easily on one line. But once we start to go into 3 factors, it becomes a lot more complicated, right? So I took everybody in the class and I asked them, how much do you like romance movies, comedy movies, and horror movies, right? And those 3 factors put everybody on a different axis for each one of those pieces. So for example, on a scale of 1 to 10, you have 1 factor, another factor, another factor, and we build more dots inside of this cube, right? Making it more complicated for the computer to process. With 7 factors, so just 7 questions basically, we create something called a hypercube. People's brains can't go past this picture, the 3 or 4 dimensional cube, but computers can. Computers can go to 100 dimensions or 1,000 dimensions. The problem is that the computer has to look through every bit of blank space inside the cube, and you'll notice that in a 3D cube, most of the spaces are blank. There's nothing in there. They have to look through all the blanks to find the ones that are good. They can't get to the Brad Pitt right away. So this is what it looks like in a 2x2 matrix, where we're comparing 2 factors, 3 factors, 4 factors, and so on. Now, the way that they solve the challenge with this using archetypes with Netflix is that they created an intersecting plane. So for example, if I like certain features, instead of trying to figure out based on white space, I try to look at, based on a particular angle inside of the cube, who else intersects with that angle? And it turns out that Vin, me, and Karen all love cricket. We don't like the same comedy movies. We don't like the same horror movies. We don't like the same genres of anything else, but we all like cricket. So we could create a class called cricket that intersects that big group of people to find out who else likes cricket. It's a way to not analyze every piece of data inside of the cube. This is important because we have, in the 3 dimensions, 1,000 points based on a 10 position array. And as we go more and more complicated, it becomes more and more complex. There are different factors we can use to simplify data called PCA. We could try to reduce them to try to use less dimensions and process the data faster. The number of dimensions, the higher you go, the longer it takes to analyze the data. We could use PCA, principal component analysis. That's the biggest one that tries to figure out what are the most important factors. Forget everything else and we'll analyze just that. Pivot tables, TSNE, or other ones to limit complexity, to look at only the factors that matter. So I want to look at only stores that are in Northern Ontario that have over this amount of sales. We don't have to look at every store in the whole world. We could just limit it to those few stores, and that tells us how the rest of it is going to go. Dimensional reduction can happen in many different ways. I give some examples of this here that's probably not very interesting to you, but the point is, I did this in R, but the point is that it shows you the intersecting plane between those elements, trying to figure out who's in the group and who's not. And I give some examples of PCA, and I look at, clustering. In this case, what clustering is doing is taking different elements that exist within a very big network, trying to identify how users are connected and what the strength of the connection to those people immediately around them and the people who are farther and how they relate to each other. I did something very similar with social media in my PhD. Same kind of idea as this, looking at how people cluster, and based on those clusters, how they connect with each other. This is one that's using cancer research to find clusters of genes. It works the same way. And there's many other dimensional reduction techniques or strategies in order to find the basic data to find out what you're looking at. And that's basically it. So anyway, the idea is that if we have really complicated data that's very high dimensional, we could try to reduce it and build a program that analyzes the most important data, and then use, in our case that we saw today, 2 kinds of machine learning. One of them is supervised data, where we say, this is a picture of a scissors, this is a picture of paper, find similar pictures in the future. Or we could use unsupervised data. Here's 1,000 pictures. I don't know what they are. You try to identify a trend between them. Often the computer is going to find some really strange trend that we didn't even know existed. For example, like the colors that are in the background of the picture of this group are the same, and we can try to figure out why. And we realize, wow, it's crazy. All these pictures were taken in Vietnam. I had no idea, based on some hidden element in the picture that we wouldn't see otherwise. All these pictures were taken in Canada, and we could start comparing these groups of pictures that we wouldn't know exist otherwise, right? So clustering a lot of times looks for unexpected connections in complicated data using parameters that we aren't able to see, right? And I'll show you an example of what that could look like with deep learning. Hold on, where am I typing? Yeah, sure, Marlon. So you could take a look at, this is the TensorFlow neural network. And it's basically the kind of idea that we're talking about today. I'll send you the link to it so you can play around with it and see how it works. And basically, you start off with a number of features. That's what we're talking about today. So in this case, X and X2, you could turn on X3, have different features or different things, rock, paper, scissors, for example. Then we have a bunch of neurons or layers inside of how the computer is going to connect this information. And then we can connect this way as well, creating different possible pathways. Ultimately, we're trying to get to this point, the output, and finding out how do the things cluster versus blue versus orange, right? And then we let the thing go, and then we start to build a simulation over time to figure out, based on this, what is the clustering. There's a point, however, when you look at these epochs that are processing, that there's a point of no return. We're not going to get any better returns after we pass that point, no matter how much processing power we use, right? More complicated problems with more complicated data can come up with more complicated things. And I'll show you an example of this in use. Let me just find it. The one I'm trying to find. Ah, perfect, thank you. The one I'm trying to find is my kid worked on this recently. He was like 17 and he built some really impressive software. I don't see it, but I'll show you a couple of them. There's something called Generative Adversarial Networks, or GANs. This is one of them that you can check out. It's called This Person Does Not Exist. And it's basically images that people that don't exist that are created using composites of thousands of different pictures, right? So basically what happens is it takes two starting points and starts comparing them and tries to find out, does this picture match this one or that one? And eventually it comes to, and the one I'm trying to find is GAN Art Generator. And I don't know where it is, but here's an example. It says, there's a cool example. I copied it in Python, I was using it. This one is, it takes the image and combines it with something else to create something else. And there's AI tools that do this very well, like GPT-3 Art Generator. And this one is called DALL-E, and it does some pretty amazing things. Like, for example, you could type in text an illustration of a baby daikon radish in a tutu walking a dog, and the computer will create these images based on a baby daikon, a tutu, etc. Build an armchair in the shape of an avocado, it will start generating these images by just trying thousands of images against each other to find out which ones work better than others. I'll show you something that I did on Twitter. Let me see. So this is my Eggs NFT account. I built a thing of Eggs NFT. Let's go into here. And you can see this one. I used the GAN in 150 iterations, and I asked it, build me a picture of a cat eating lettuce. So it started to build pictures of cats. It started to build pictures of lettuce. And then it built me this picture of a cat mutant lettuce. I don't even know what this is, but it's not a picture of a cat eating lettuce. It would have to run for thousands of more iterations to figure out, does this closely resemble a cat? Does this closely resemble lettuce? And then eventually get to the point where it says, okay, I'm 100% certain that this is a cat eating lettuce. And this is just the extension of what we can do with AI and a whole bunch of other pieces. This uses, again, to develop images. But there's a lot of different types of artificial intelligence that do this kind of thing. If you're curious about NFTs, we can talk about that a different session. This is one that I put together on OpenSea. I started uploading pictures of my breakfast, creating NFTs. And when we had a class about how to make them, and basically you can buy these tokens that are pictures of eggs, and I just uploaded them online. If you're interested in NFTs or cryptocurrency, this is the only one that I know of that's based on eggs that I made. So take it from there. But basically, if you create, the idea that I was working on this summer is take art that's automatically generated, build them into NFTs in a pipeline, and have something that's going back and creating them as they go. If people are interested in buying them, fantastic. But you could do things like cat eating lettuce, which doesn't exist otherwise, and it creates a photorealistic picture. Something I was playing with. But the bottom line is that if we have a lot of complicated data that we have to sort in different ways, and we don't necessarily have an algorithm to do it, machine learning is a really good option because it can do trial and error, it can do reinforcement learning, it can do supervised or unsupervised learning to try to find the answer. This is used a lot in robotics. So instead of programming a robot to say like move 5 degrees, move 7 degrees, tilt this. You could just say, here's the beginning point, here's the end point, figure out all the steps in between. And we could build a program that will iterate through over and over and over again saying, is the coffee spilled? Does it look like this? Based on the pictures or images or motions that we provide it. And the computer will learn how to mimic it by writing thousands of lines of code itself. Another way that we can use machine learning to figure out how to program a robot, how to make a program work. If people are part of the cluster or not, we could use this for fraud detection using like credit cards and thousands of other things, right? So it's really, really useful. And it's a different kind of programming, but uses all the tools that we're using. Anyway, I just talked for 1 straight hour. I hope you are all doing amazing this Friday, and the week is almost over. You made it through another week. Congratulations to you. Questions, comments, thoughts?
Thank you.
Nice to see you. I hope some of this is interesting. I highly recommend check it out. If you go into the machine learning for kids, there's like 1,000 different worksheets that you can go through and build projects that you can control a video game by moving your head, by doing rock, paper, scissors. You could program all kinds of things. You could build the hot dog cell phone program pretty easily, right? You could build basically anything you could think of that recognizes images or sounds. And I'll leave you with a good thought. There's a project that for people who are deaf, they wanted to hear, get a text message on their phone if their monitor, their IoT monitor in their house heard a sound like glass breaking, baby crying, water running, stuff like that. You could build that by recording some background ambient noise, recording a database. There's a company that used YouTube to do this. Find every clip of a baby crying. And then if a baby's crying, it will send them a text message based on that huge database. It can recognize the sounds. And then it's able to figure out and alert the person if something's going on, glass breaking, etc. So there's a lot of cool ways that we could use this technology to build products that really help people. See you later. Have a good one.
Thank you. Bye, Sid.